In this part of the video, we are going to attempt to obtain a spectrum analysis of the Hoyland device. It is now powered up. The tube is lit, and we come over here. We're not feeding it any modulation right now. The audio modulator is turned off, so we're just seeing a RF signal. We're just seeing the RF carrier on the waveform. The RF carrier is running right now at 4.66 megahertz, and the oscillator in this device is being fed with a high voltage power supply that has an AC ripple running on it, and so you're seeing the AC ripple running across the top of the RF trace. If we adjust our time base to look at the RF, we can see there's your RF sine wave. And then if we broaden the time base back out, you can see the whole envelope with the AC ripple riding on top of it. At this point, the tube is lit constantly. It is not pulsing, and there's no pulse showing up in the RF waveform. If we turn the modulator on, the modulator is actually set for 10,000 hertz. When the tubes warm up in the ICO or audio generator, the tube will start pulsing. There it goes. You can see it pulsing on and off. I believe that since you can see this with your eyes, the pulsing isn't that fast, and so I think the tube is actually deionizing in between each pulse. If we come back to our scope here and we adjust the time base, we can see the pulsing action has appeared in the waveform. I'm going to try to adjust the triggering so that we can see each individual pulse. It's hard to stop. Now what you're seeing is you're seeing each individual pulse envelope, and you're seeing the AC ripple riding on top of the pulsing. And if we look closer and closer at the waveform, we can see the audio mod riding on top of the waveform also. That's your audio mod. And if I can get the triggering adjusted correctly, I can get it to we can see each envelope part of the pulse. If we come back up here and look at our frequency, we can notice that with each pulse the frequency is being pulled down. And now we started off at 4.6 megahertz, and the pulsing is pulling it down to 3.5 megahertz. If I adjust the machine so that it pulses faster. Okay, I'm back. I've adjusted the settings on the machine so that we can see each individual pulse, and there it is. That is the machine with a constant pulsing action. That's what the tube looks like. The frequency tester actually settled in at 2.1 megahertz. So with the machine constantly pulsing, it's running 2.1 megahertz. You'll notice the pulse is short duration, and you can see part of the AC sine wave riding on top of the pulse. If I close in with the time base, you can see our 10 megahertz riding on top of the pulse. That's the modulation. So that's our Hoyland pulse right there. Let's go over to the frequency spectrum analyzer, and here's our spectrum coming off of the Hoyland. It seems to be blinking off and on. It's not a constant spectrum. It seems to have its peak at the 4.85 megahertz region. I'm going to put a hold on this and stop it. There it is. Now we can analyze our spectrum. Okay, we're back with the spectrum that we've derived off of the SCUM replica of the Hoyland design. We're going to select cursor function and see what that fundamental is. I'm going to bring the cursor over and land it on that fundamental. When the notch lights up, that's when we know we've struck the signal. There it is. So that's a high amplitude notch, and that shows us that our fundamental is at 4.69 megahertz. I'm not seeing any signal before that. It looks like the signal's all appearing after the fundamental, and we have the next signal is here and the next signal is here. Let's see what those frequencies are. That is 4.36 megahertz. That is 9.36 megahertz. And the next one is 13.9 megahertz. The next signal is 18.7 megahertz. The next signal is 23.5 megahertz. The next signal is 27.7 megahertz. The next signal is 32.7 megahertz. Next signal is 37.3 megahertz. The next signal is 42.5 megahertz. And the next signal is 46.9 megahertz. Okay, let's close in on the frequency spectrum, and we can see that we're getting signal all the way up to about 100 megahertz. It's very low at that point, but there it is. If we adjust the voltage, no, that's all noise right there. No, we're getting a noise signal at below 1 millivolt. There, okay. Below 1 millivolt, so I'm going to adjust it back up. Okay, there's no noise there. I'm going to bring the cursor all the way over to the edge, and we're going to attempt to look at a live spectrum. I'm going to turn the machine back on. Okay, here's our spectrum, and if I turn the machine back on over here, the tube's running. Here's our signal on the scope. You'll notice that each pulse initiates on the amplitude peak of the audio modulation. We can tell that this tube is pulsing away because it's experiencing oscillator pulling action, which is dragging the RF carrier down in frequency from a beginning of 4.8 megahertz all the way down to we're at 2.09 megahertz now. Now if we come back to our spectrum and just view it in live action while the machine is operating, there is our spectrum. It actually has a signal down at 1 megahertz, and we're seeing our fundamental, that's that big tall signal, at somewhere around 5 megahertz. The each pulse actually initiates at a good RF oscillator frequency of somewhere around 4.8 megahertz, and then as the pulse envelope continues, the frequency gets pulled down. And with the spectrum analyzer, we can see the full spectrum in action, and that's a Hoyland spectrum that you're seeing right there. Now I'm going to, once again, I'm going to hit the hold button, and let's explore that spectrum. I'm going to come back over here and turn the machine off. There you go. Okay, just one more. Let's see what we have here. We have the light shining on the spectrum analyzer. I want to get that off. Okay, here we go. I'm going to select the cursor function and bring the cursor on over and just hit that first frequency around 1 megahertz, and let's just identify it. So this will be a lower sideband, and there it is. That occurs at 936 kilohertz. The next frequency line that we can identify is 1.87 megahertz. The next line, and these are all lower sidebands, is 2.7 megahertz. That might be a pull down frequency. That might not be a lower sideband. And the next frequency is 3.73 megahertz. The next frequency is, here's our fundamental, 4.69 megahertz. So that's where the oscillations are starting. The next frequency is 5.53 megahertz. The next frequency is 6.52 megahertz. We have 7.44 megahertz. Yes. Let's just keep on going. 8.48 megahertz. 9.36 megahertz.